Hey there, and welcome to another video. Our last video, in fact, on exact differential equations, and we're going to talk about it. So let me preface this with saying, if you haven't watched the last two videos on what exact differential equations are and how to solve them, you really need to do that, because I'm not going to go explain what those are again. What we're going to do is look at a very specific technique on how to solve some differential equations that aren't exact yet. And we'll talk about an integrating factor, and we'll learn that if we can make an integrating factor with just x's or just y's, it's very easy, very nice, and will change something that's not quite an exact differential equation into something it is. Now, you might have remembered we've used integrating factors before. We did on some previous differential equations several times, but now we're going to apply them to exact differential equations and see what they look like. So again, watch those videos if you haven't done it, and then come back and see this one. It's very interesting, but you need a lot of background because I'm going to be using some terminology that if you haven't really heard or seen of exact differential equations is not going to make a lot of sense. So we're going to jump right into it and explore what this is. I'm going to go through a lot of theory at the beginning, then 3 examples to show you exactly how to work it. So what if you got a differential equation and it looks like it should be exact? And that's why I say, what if an exact differential equation isn't exactly exact? What if you have this and these are not equal? So what if you took the partial derivative of m with respect to y and the partial derivative of n with respect to x, and it's not coming out the same? So the mixed partials are not the same, saying this is not an exact differential equation from some sort of potential function that's continuous and differentiable on some sort of a region. So what if that's not true? Can we make it true? Can we multiply by something that says, hey, what if I multiply on both sides by some function of x and y properly defined to make this thing an exact differential equation of some sort of potential function? So, well, is that possible? Let's find out. Let's see if it's possible. Theoretically, it should be possible all the time. So what if we multiply by some function, let's call it u, on both sides so as to make this a differential equation that is exact. And so what I'm going to do here is I'm going to show you that what we want to happen kind of drives what we're looking for to make this equation into an exact differential equation. So let's start looking at that. So if we multiply both sides by some function of u, I'm going to get a u here and a u here by distribution, and 0 times some function of x and y is still going to be 0. So our function u times m dx plus our function u, this can be in terms of x and y right now, we'll talk about that later, times m dy still equals 0. What we call that u of x, this function in terms of, u of x and y, this function in terms of x and y, or what we're going to learn later is that with both x's and y's, this would be very, very difficult. So we're going to look at the cases where what if you can get exactly just x's or exactly just y's? That's a lot nicer. So what that u of x and y is called an integrating factor. It's something that, that lets us slightly change the form of a differential equation from what it is into what we want it to be. Now, we did it several times before in a few different sections, but now we're going to use it for exact. So, very quick recap, just to make sure you're with me. I know that you've just watched the videos, so you should be, but just make sure. So we have this thing that we really want to be an exact differential equation, and if it is, the mixed partials have to be equal. If you check it and they're not equal, that means that is not an exact differential equation or total differential of some sort of potential function. So we're thinking, how do we make it possible? Let's multiply by something that forces this to be possible. Is that even possible? Can we even do that? Well, let's think about what we want to happen. What we want to happen from our new form. So this theoretical function that we multiplied, let's think about what we want to happen. What we want to happen is for this to be sort of our new m, and for this to be sort of our new n. So we still want the partial derivative of this entire piece with respect to y, we want that equal to this entire piece when we take a partial derivative with respect to x. Does that make sense to you? I mean, do you get that? That if we multiply by some sort of a function to make it exact, it's still going to meet the properties of being an exact differential equation, which means I need my mixed partials to be equal. I need to be able to take this first piece, and this just stands for some function of x's and y's. Okay, I need to have this partial derivative with respect to y to equal this partial derivative with respect to x, and then we can guarantee that that was some sort of an exact differential equation. I still need that to happen. So I still need to be able to take the partial derivative of this piece, this function in terms of, oh yay, look, x's and y's. I still need this partial with respect to y to equal this partial with respect to x in order to guarantee that this is of the form of an exact differential equation. It guarantees it's coming from some potential function that we can find. So, now what in the world would that looks pretty crazy, first of all. And at the end of this, I'm going to give you some better notation. But right now, it's important to see that this is in terms of x and y, both of them. And so we're going to have to deal with some partial derivatives. What we're going to go on and do in a minute, because there really shouldn't be any suspense here in math, what we're going to do is we're going to see that at the end of this, if I say that, or kind of in the middle, if I say that, well, what if this was just with respect to, or just in terms of x, would it make it better? Or just in terms of y, would it make it better? We're going to see yes, and so we can simplify this a little bit. But for right now, to get the feel of it, here's what we would want. We would need for the partial here with y to be the partial here with x to guarantee exact. Now what do you see? What do you see? Do you see that you have a product? And do you see that you have a product? You're going to need to use the product rule. So what we're trying to do is we're trying to solve for u. We're trying to get some function of u that we will be able to know explicitly. We're trying to find that. But in order to get down to the u, it's all wrapped up in partial derivatives, wrapped up with all sorts of stuff. So let's take the partial derivative of this side with respect to y, this side with respect to x, because that's what we want to be equal. Let's do it. So the product rule says, hey, let's take the derivative of the first. I'm going to drop the x's and y's, but this still is a function of x and y right now. Partial derivative of u with respect to y. So derivative of the first times the second plus the first, which is just our u, times the second, the partial derivative of m with respect to y. We're just using a product rule, derivative of the first times the second plus the first times the derivative of the second. We'll do the same thing on the right-hand side. The partial derivative of the first times the second plus the first, which is just u, function of u, times the partial derivative of n with respect to x. So we've said this is what we need to have happen for an exact differential equation to be exact for some potential function. We've said, well, let's try to solve for u, and that's what we're doing right now. We're trying to solve for u. Okay, well, if I'm trying to do that, then maybe I need to actually perform the partial derivative here and do the product rule. All right, so if I'm trying to solve for u, it makes sense to maybe let's group our u's on one side and group everything else that doesn't have u's on the other side so we can factor. So let's do that. Let's subtract this over here, subtract this over here. So moving some things around, I'm going to keep my u times the partial derivative of m with respect to y, and that's going to stay there, minus the u times the partial derivative of n with respect to x, that's going to stay there. On the right-hand side, so I kept this, I subtracted this from both sides. I'm going to keep this on the right-hand side, partial derivative of u with respect to x times n, minus this. Partial derivative of u with respect to y times n, just some algebraic manipulation. We're grouping our u's. So u's on one side, everything else on other. You're going to subtract two terms here. Now let's try to factor. So if we factor out the u, partial m with respect to y minus partial n with respect to x. On the right-hand side, same thing. We're not going to change that, but we are going to talk about it right now. Why do we need to talk about this? Because that looks really nasty. Now, theoretically, yeah, you could solve for u, couldn't you, just by dividing? But look at what's happening. You've got a whole bunch of partials, all with u's in them. You've got a u that's going to be solved. It's really, really ugly. Theoretically possible, yeah, but very, very difficult to actually make work effectively and often. And so what we're looking for is, man, what if we? And granted, this is a special case, but what if we were able to find a u with just x's? So if I look up here and say, well, what if I don't have a y? So exact, no. Multiply, sure. It would look like this. Well, what do I want to have happen? Partial here with y, partial here with x. But what if I chose a u that didn't have any y's in it? So what if our u only had x's? Would that make a difference? Would that help us? What if you only had x? So no y's. Think about what would happen. If I took a partial derivative of this with respect to y and this with respect to x, but you only had x's and had no y's whatsoever, this would still be valid, that'd be fine, because m can have x's and y's. This would be fine, this would be valid, because n can have x's and y's. Partial derivative of u with respect to x would be fine, because u would only have x's, but look at this, the partial derivative of u with respect to y. If u only has x's, do you remember this? Man, I hope you remember this, that if u only has x's, no y's at all, and you take a partial derivative of a function that has no y's, with respect to y, everything would be held constant. It'd be like saying, hey, take the derivative of this with respect to y. And you're going to go 0, 0, and 0. It's 0. Exactly. So if we choose a u that has just x's, then this piece becomes 0. 0 times m is still 0. We basically annihilate that whole entire term. Do you get that? Do you understand that if u has just x's and no y's, that the partial derivative of u with respect to y would have to be 0? That's an important concept to understand. So we're understanding that if u has x's, that thing's gone. That's pretty cool. That's going to simplify this. A little bit later, what I'm going to say is, what if we had chosen to have u equals only y's instead of x's? Well, then this piece would be 0. And so I'm going to give you two different formulas, one of which occurs with what we're doing now, if you use only x's and no y's. But the other one would be, what if you came back to here? I'm not going to show both. And what if you had y's but not x's? Then this would be 0, and we're just going to basically flip-flop a couple things. It's not going to be that bad. I promise it's not. This is just all the theory behind it, because when you see this formula in your textbook for the first time, you go, what in the world is that? It's not that bad. What you're doing is you're saying, I need this to happen for exact differential equations. Let's solve for u as much as we can, and let's make a restriction on it. Let's say, to make this nicer, to make this possible really for us, let's assume u only has x's. Then this is 0. Well, what do I do now? Well, hopefully you're with me still. If not, go back and rewatch that minute. What do we do now? Now we make one other little alteration, and it's right here. And this is important for you to get. If u only has x's and no y's, not only would the partial derivative of u with respect to y be 0, because there's no y's, all the x's would be held constant, but the partial derivative of u with respect to x is no longer a partial. Because u only has x's, you're literally finding the derivative of u with respect to x, not a partial derivative. Do you get that? So like if that doesn't have any y's, you don't need to take a partial. It's just literally, hey, take the derivative with respect to x. No problem, 3x squared plus 1. That's not a partial derivative. So this becomes du dx. That's nice. Well, why is that nice, Leonard? That didn't seem so nice to me. It looks about the same garbage. Well, hey, if u only has x's, you just got rid of a whole term you didn't know how to deal with. But secondly, you changed a partial derivative of u with respect to x, because it could have had y's, into a derivative of u with respect to x, because if you guarantee it only has x's, then that's now not a partial. You go, why is that important? Let's rewrite it and let's look at it. Also keep in mind, we're trying to come up with a formula. We're not trying to get one u for everything, but a formula on how to find u. And so we're going to have some ugliness that's actually very nice. Notice this too. I want you to see it when I give you this different formula, that this is found already, and this is found already when you check to see if your mixed partials are equal. So you go, hey, you know what? This, you would have checked that, wouldn't you? And this, you would have checked that too. So that's already on your paper. Not even hard to find. On the right-hand side, we get du dx times n. Now keep in mind what n is. N is not really a variable. And this is sometimes where students get a little bit confused on the notation. Keep in mind that m and n are functions of x and y. So it's not a variable like p or something that you would say, I need to do separable equations here, separable variables. N right now is a function of x and y, all right? So what the variables are that we're treating are x and u, because if you look at this, and this is just brilliant right now, this is a first derivative of u, our variable, our dependent variable of x, our independent variable. So wait a minute. If that's a variable and that's a derivative, you're telling me this is a differential equation? Yeah. Because we held x constant, and I know there's a lot of theory here, but because we held x constant, we were able to change this partial into a real first derivative. And if you solve for that first derivative, you can get, I mean, look at it. If you got the first derivative of u with respect to x, and you got a u over here, and all of this other stuff is in terms of x's and y's, then can't you do this by a separation of variables? Can't we get our u du on one side, or x dx on the other side? Remember, n and all this stuff has x's in it. Let's just group that, and let's see what happens. So what I'm going to do right now is I'm going to switch sides, because we typically, in every example we've had our u du, du dx on one side, our derivative on one side, and all the things on the other side. So I'm going to switch that before I start moving a whole bunch of things around. Okay, I'm going to go through it one more time, because every time I teach this in front of real students, well, I guess you are real students, right? Sorry. Every time I teach this in front of students who are watching this for the first time, there's always a question about that. They go, why is this possible? So last time all the way through, because you need to get it in order for you to understand why this equation I'm about to give you works. So what if exact's not exact? What if your mixed partials are not equal? Multiply by something. Okay, great. What do you want? You want the mixed partials of this new differential equation to be equal. That's what you want to happen. What we're solving for is the u that will force this to happen. And we go, okay, product rule, no problem. Maybe group our u's, because we're trying to solve for u. Awesome. All right, we get this. We look at it and go, that's really hard. That's really difficult, because I have partial derivatives of u with respect to two different variables. And then we say, well, what if we consider two cases? Case one, where there are only x's. Then a partial derivative with y would be 0. And this would no longer be partial. The second case is, what if you only had y's? This would be 0, this would be not a partial, and that would give us our second equation I'm going to give you in just a moment. So, all right, well, oh my gosh, if that's not a partial, that's a first derivative with respect to x. I have a differential equation, and now we're solving it. We're saying, all right, this is awesome, just like day one with separable equations. So, all right, what do? Well, we get our du dx on one side, and then what we're going to look at is say, let's try to get our u's du and all of our x's, or stuff that has x's, dx on the other side. So we got u, oh, there's a u. Maybe we divide both sides by u. And then we want all the junk that has x's. That has x's. That could have x's. This could have x's. So we're going to keep this. over n dx. I'm looking at it, it's a first order differential equation. This is treated as my dependent variable, this is treated as my independent. So I'm getting my u's du divided by u. I'm getting my everything that could possibly have x's. All of these x's, this could have an x, so all of these x's dx. Understand, this is where the question comes from. What is n? Is n a variable? No, n is a function, all right? N is this little piece that has x's in it, potentially. And so we're going to have that. This is a function that has potentially x's, and so are the partial derivatives. So we group everything that has x's dx, we group our u du, and we go, oh my gosh, man, this is like close to day one, which is really neat that something as advanced as this is from day one. We do an integral of both sides, and we say, hey, ln u equals this integral. And I'm not going to solve it. There's no way to solve it right now. I don't know what these functions are. Remember, we're getting a formula, and so we're keeping it as general as possible. The only thing that we've said, the only restriction we've said is that, well, what? What's the only thing we've said about this process so far? We've said that my u only has x's. So remember that. My u only has x's. We're going to check for that in our first example. They go, okay, that's still really nasty. I've got this ln u. How do I get rid of the ln? And you go, oh, yeah, I would need an exponential. And man, this is really cool. When you do an exponential, we would, on both sides, so e, you would get u equals e to the integral of nasty stuff. You go, that looks really familiar. Do you remember integrating factor of rho? And it was e to the integral of px. Do you remember that? That looks very similar. So here's what we've done. We've said this is the u that's going to be necessary to actually make this thing turn into an exact differential equation of some potential function, because our mixed partials would be equal if u equals this. That's rad. That's awesome. The only restriction here that you need to write down, and you really need to understand this is for a u with no y's, x's only. A u with no y, only x. How it would change, and then I'm going to give you a shortened version of this. How it would change is this. If you had for no x's, only y's, we'd still get an e, we'd still get an integral. All that happens is that you would actually flip-flop these, and that would be an m. Hopefully that makes sense. Maybe you can walk yourself through that. You'd still have an m, you'd have an m and not an n. So this would be 0, this would not. You'd end up dividing by m. Do you see it? Also, you'd have this, because that's a negative, we'd have to flip something around to get that not be a negative. So you'd end up dividing by negative m, or you'd solve this in a different order than I did, and then these would be out of order. So for a u with no x's and only y's, we'd change this, and that would be an m. And of course, we'd have a dy. Why? Well, if this was 0 and this wasn't, if we had only y's and no x's, well, then gone. And then this would be a du dy, and we'd integrate with respect to y, obviously, because we have only y's where we had only x's here. This is for no x's, only y's. Now the process is actually pretty easy. What we're going to be doing is we're going to look at this and say, hey, let's check our mixed partials. If they're exact, we're done. If they're not exact, let's do a comparison. Let's see if this gives us only x's, or if this gives us only y's. And so we're going to do two different things. We're going to subtract partial of m with respect to y minus partial of n with respect to x over n, and see what that gives us. If it has both x's and y's, it's not a good choice. And then we're going to reverse it and do partial of n with respect to x minus partial of n with respect to y and divide it by m. And if that gives us either, well, we'll see which one gives us just the variable we're looking for. And whatever one works, that's the one we're going to go with our integrating factor. We'll take e to the integral of that, and then we multiply the whole we make it an exact differential equation through that multiplication. Now, I promised you I was going to make this a bit easier, but I want to make sure you see it. I want to make sure that you're okay through here. So if you're not, you really need to understand the product rule, the, hey, make u x's only, get rid of a couple things, that changes to an actual derivative with respect to x. That's an important concept. It's no longer a partial. And we do the reverse for this one. So how to make the formula easier? Because, man, when you look in the textbook, this is basically what they're going to give you right here. They're going to say that's what you do, and that's true. But maybe to make it a little nicer, what exactly is the partial derivative of m with respect to y? It's the thing that you check right here. It's the same thing. So when you even check, which is your first step, to see whether or not you have an exact differential equation, you are doing this right off the bat. So it's not extra work minus, and you're doing this right here. That is what that is. So you're checking your mixed partials right off the bat. So to find your integrating factor, really all you do is you subtract them and you divide by the thing where you got your last partial. So partial y minus partial x, and then divide by partial of m with respect to y minus partial of n with respect to x divided by the n. And then this right here, if this is in terms of x's only, you take an integral with respect to x, and you take e to that. For x's. Or for y's, what would happen? Well, then our integrating factor would be e to some integral, but it's the same thing in reverse. That right there, this is your mixed partials right there. This is the partial derivative of n with respect to x minus the partial derivative of m with respect to y divided by the m this time. And then with respect to y. That's how I really would like you to think of it. I don't want this to be crazy hard. I gave you the crazy hard stuff to show you why it works, to show you that we guaranteed that it worked. This is really a proof if we show that there are no y's, or vice versa, there are no x's, that this is going to be an integrating factor that's going to make this work. We guaranteed it because we said, let's multiply by it. Let's show that's what we want to happen. Then we solve for the thing that's going to make it happen. We solve for the thing that's going to force this to be an exact differential equation. Really neat stuff. And we said if this is true with no y's or no x's, then we can find that. It will be an exact differential equation of some potential function, and we can go and solve it with the techniques we already know. So the solving part of this is going to be very, very fast. I spent a long time going through that proof for you, but now how you think about it should not be this difficult. How you think about it should be, I'm going to check my mixed partials. So this is the thought process. I'm going to check my mixed partials. If they're equal, I'm good. Okay, I'm going to use the techniques I learned in the last two videos. If they're not equal, what I'm going to do is I'm going to start with this one. X's are generally easier for us to kind of think about. I'm going to start with this one. I'm going to subtract my partials. I'm going to divide by n. I'm going to see if it gives me something with only x's. If it does, I'm going to multiply everything by e to that, e to the integral of that. If it doesn't, then I'm going to do it this way. I'm going to say, okay, let's reverse it. Let's subtract them in an opposite order, and let's divide by m this time. And if that gives me something at only y's, then I'm going to integrate e to that, multiply my function or my differential equation, and get an exact differential equation that's going to work. So what I'm going to do, I'm going to rewrite these on the board. We're going to go through 3 examples. Just one at a time. The checking is the hardest part, the integrating factor, understanding which one you use. Once we get done with the video, it will be very obvious, but at first it's kind of difficult to see that. And so we're going to spend some time on that, and I'll be right back. All right, I'm ready. I hope you're ready. Let's go through this and let's learn how to change something that's not an exact differential equation into one that is. So let's take a look at it. Is it an exact differential equation? You can't say that just by looking at the form. That's not the way this works. We have to check the mixed partials to make sure it's coming from some sort of potential function that is continuous and differentiable in some sort of region. Right now it's not. And let's show that. So I'm not going to write out the m and partial derivatives explicitly. We did that in the last few videos, and that should be very comfortable with you. What we're looking for now is we're looking to understand how to get this to fit that exact differential equation model. So I might write something like, that would be my m. And that would be my n if this were an exact differential equation. We're going to check the partials right now. So is the partial derivative of m with respect to y, which is 2x, equal to the partial derivative of n with respect to x, which is negative 6x. And you go, yeah, no, those are clearly not the same. What that means, this is not an exact differential equation. These are not equal. Also, if you like the notation of partial derivative of n with respect to y, or partial derivative of n with respect to x, that's fine. It just gets a little bit cumbersome to write, but that's exactly what these things mean. If you like that formula better, that's fine with me. I personally, because we have to write it a lot, I'm going to use that m subscript y to represent the partial of m with respect to y, and n subscript x to represent partial of n with respect to x. So these aren't the same. So you're what, man, if that's not an exact differential equation, how in the world can I make it work? Can I find an integrating factor? And we went through that whole process. So here's the idea. We're going to start with this one, and we're just going to see, hey, if I do this, am I going to get a function with only x's? If so, then I use that. If not, I'm going to do this one and say, if I do this, do I get a function with only y's? And if so, then I use this. So it's kind of like a check. I start with this one because we're more comfortable with respect to x sort of things. So I'm going to start with that one. Let's check to see if the derivative of m with respect to y minus the partial with respect to x of n over n. Well, let's see what that is. So for us, all we're doing, we're not doing anything new. All we're doing is we're saying, let's take this piece minus this piece divided by this piece. 2x minus negative 6x divided by y squared minus 3x squared. Some of you will get very good at this very quick, and you'll be able to do it in your head, and it's not that hard. Because when you look at it, all you're checking for is whether you're going to end in all x's here. Is there any way to get rid of that y, like at all? Well, no. Then this is not a good choice, because no matter what you do, and don't try too hard. It's hard for me, a math teacher say don't try too hard, but don't try so hard to make this work into only x's without, just some simple factoring should do it if it's going to be possible. So that would be 8x. That would be something with a y that's not going to cancel. You cannot factor that very easily. And so we say, no, this is not a good choice for us. So not exact, but this is not giving us a function of u that's just in terms of x. So let's try the other one. Let's do, so x only did not work. Nope. So let's try y only. If we're going to have a function of y only, it's got to fit this model where I have partial of n with respect to x minus partial of n with respect to y divided by m. So in other words, you flip-flop it. This piece minus this piece divided by this piece. And like I said, sometimes you're just going to look at it and say, hey, this is going to work out real nicely. Because what we want, and this is not an x, this is a no. What we want is for everything except for our y's to cancel. So here you want only x's, here you want only y's. And we see that that's going to work. So this gives us this negative 8x over 2xy. Oh my gosh, that's nice. This is negative 4 over y. Now, listen, this is not your integrating factor. What you have to do is say, all right, now that I've determined that there is a function in terms of just y, as a matter of fact, this right here says that's only in y's, I can straight up integrate that. You found the inside of that integral. So what we know is that if our u is e to the integral of the derivative of n with respect to x minus the derivative of m with respect to y all over m dy, you've now found this piece. That piece right there, that is negative 4 over y. So this is not your integrating factor, but what it does, it gives you the ability to integrate pretty easily. It's going to look very similar to linear. With respect to y, that's the only variable we have. That would be, well, negative 4 ln y e to the ln of 1 over 4. No, it's not. Ln to 1 over y to the fourth. And so we're going to get u equals 1 over y to the fourth. We've done this many times. I know I'm going through it fairly quickly, but this is really old stuff as far as doing this piece of it. So again, since it's our first example, you check. You just check. It's the same thing you do anyway, right? So check to see if you have an exact differential equation. Mixed partials. If you do, don't do any of this garbage, man. If you don't, try this minus this over this. If it's only x's, you're good. If it's not, try this minus this over that. So the opposite way, exactly. If that's only y's, you're good. Integrate, take e to that, and that right there. So this is the inside. Integrate, got it. Take e to that. Simplify, that right there is your integrating factor. Let's see how this plays out. So if that's your integrating factor, where we started was right here. And if we multiply everything by that integrating factor, man, not negative 4 over y, but e to the integral of that. That's how the integrating factor works. We just found the inside piece. Integrate e to that. Gives us an integrating factor of 1 over y to the fourth. Let's multiply everything by 1 over y to the fourth. Again, you're going to get that statement of make domain restrictions where appropriate, or assume that what you need to have is not 0. So we know y can't be 0. And if we distribute everything here, we're going to get this 2x over y to the third plus, I'm distributing here and here. Remember, this would distribute here, but you multiply through that. 1 over y squared minus 3x squared over y to the fourth. And yes, you need parentheses here. dx, dy, and still 0. You know what you should do now, just for your own edification, just to see it. Take the mixed partials again. This is your new m. With respect to y, let's see, that would be 2x, y to the negative third. I bring down the negative 3, that's a negative 6. X, y to the negative fourth would be over y to the fourth. And this would be your new n. With respect to x, that would be, 0. Look at that. With respect to x, that would be negative 6x over y to the fourth. What the heck? That actually works. This guarantees you that integrating factor, because we proved it, that guarantees you that if you can make the first one with x's only or the second one with y's only, it's going to make an exact differential equation for you. That's awesome. Theoretically, if you use both variables, it happens all the time. But here you go, hey, that worked. That's now an exact differential equation, and you go through it exactly the same way that you learned in the last 2 videos. So the way that we go through this is that we look at which one of these would be easier to integrate. Are you going to integrate this with respect to x or this with respect to y? This looks way easier to integrate with respect to x, so we're going to pick that one. Remember what this is. This now is the integral of the function we're looking for, the derivative of the function we're looking for with respect to x. Which means that our function itself, well, that's the integral of this with respect to x. And that's really nice. That means that we're going to get x squared over y cubed. But we're also going to get some sort of a function that could have y's in it. Remember that, man, this is the first derivative of a function with respect to x. An exact differential equation guarantees that. So if I do an integral and undo the x part, so with respect to x, I'm going to get a very easy integral to do, but I'm going to get a function of y, sorry, it's not derivative yet, thinking the next step, a function of y that if I took a partial derivative of this would go to 0. Since this is based on a partial derivative with respect to x, we have to show that any constants that any terms that had y's in them would be held constant. Now, the next step is, let's take a partial derivative of f with respect to y. Well, that would be that whole negative 3x squared over y to the fourth plus the first derivative of g with respect to y. And the reason why we do that, we integrate m with respect to x, take a derivative with respect to y, and set it equal to n. Because that's exactly what this means. This means, hey, this is the partial derivative of f with respect to y. Okay, this is the function of f that we're looking for. Take the derivative with respect to y. But when we do that, we know that that also has to equal this piece. Also has to equal our new n, if you will. So those things being equal, if we subtract or add that negative 3x squared y to the fourth, this is gone. And our first derivative of the function of y that we don't even know, we know the first derivative now. We know that this is 1 over y squared. So how do we undo derivatives? Let's do an integral. So the first derivative of g with respect to y is 1 over y squared. If we integrate with respect to y, then the function of g we're looking for, the missing function from right here, well, let's see, y to the negative 2, add once negative 1 over the new exponent, so that's going to be negative 1 over y. We don't need the plus c because this is going to be a function of x and y equal to a constant anyway, and it would just absorb any other arbitrary constant terms that you would have. So we don't really need to show that. What we do need to show is that our function that we had, after understanding it's not exact, x's only don't work for an integrating factor, y's only do work. So we took this in the proper order. We got negative 4 over y. We integrated. We took e to that. We found an integrating factor. We multiplied everything by it. It became exact. We said, all right, that's fantastic. What's easier to solve? Well, solving an integral with respect to x here was easier, so we took our m. Notice how the integrating factor being y's only had nothing to do with what we chose over here. All it did, it made an exact differential equation for us. It does not affect the rest of it. It's just the first step. From here, you do everything the same as what I've already taught you. So we say this integral is easier. Take the integral of m, that's m, with respect to x, great, function of y. Derivative with respect to y, great, equal to n. Solve for the derivative of the piece you don't know. Integrate, we found the piece, now we go back to the function we already knew. But we now know what that function is, that missing piece, in terms of y only. Is it always going to be in terms of y only? Yes, the g, will be in terms of y only. And we know that's equal to a constant. So we'd have this x squared over y cubed minus 1 over y equals c. And if you had an initial value, that's where you plug it in. And I think that's about all I really need to show you. The next two we're going to go through probably a little bit quicker because I did sort of re-explain some of this stuff. But the long story made real short is don't confuse finding an integrating factor with actually performing the solving of an exact differential equation. This is just setting up the proper form for you. Find the thing you need to multiply to make it happen. After that, from right here, you're basically ignoring this. You're saying that's not a substitution, you just multiplied by something. So this works exactly like the last two videos. Pick the part that's easier to integrate, either m with respect to x or n with respect to y. Integrate the easier one. Whatever you integrate with respect to, you're going to have a function in the opposite variable that you don't know that would be held constant under a partial derivative. Take a derivative with respect to that variable, a partial, and set it equal to the piece that you didn't, opposite of the piece that you just integrated. So with m for an integral equal to n with a derivative, and then we solve for that missing piece. That's about it. I'll come back with a couple more. I'd really like you to try the next one on your own. So when I start introducing it, maybe pause and try it. Okay, let's give it a shot. Hopefully you can pause right now and try that yourself. Well, actually, hang on. Wait, before you, hopefully you haven't paused it already. Before you do that, because exact differential equations have a plus between the two components that you have, you might see some people asking you to do this first. While not extremely necessary, you might see this. And what that tells you is that, okay, just remember that when you take the partial derivative of this piece, it's including that sign. And that's why they would have you do that. So now you should pause it. I want you to just test, see whether that's an exact differential equation or not. And if it is, great, you're done. If not, see if you can find the integrating factor. Of course, we're going to start that right now. So how to go about doing it. If this were an exact differential equation, which it isn't actually, then what would happen is that this would be an m, and that would be an n. And we would say, okay, the first thing we do is we test it. Let's test the partial derivative of m with respect to y, and the partial derivative of n with respect to x. M with respect to y is 1. N with respect to x is -1. And you go, man, I really can't, Leonard, can you just please change it to a minus? No, would ruin all the fun, guys. So no, you can't do that, all right? This is not exactly the same. And for an exact differential equation, the mixed partials would have to be exactly the same. That's why it's so important to understand that that sign goes with that term. That's why I introduced that to you. So is this an exact differential equation? No. Can we find an integrating factor to make it exact? And yes, that's our next step. That's what we're going to try to do right now. So what we're going to do is we're going to do a little test, and we're going to take this piece minus this piece over this, or this piece over this piece. I said minus, I made a mistake. This minus this over this, or this minus this over that. In your head, do you see it right now? Do you see that this minus this over that will have no y's? This minus this over this will have both x's and y's. What's the best choice? This minus this over that. If you're not clear on that one, maybe think about that for a second, or just try both. So we're going to start with, for x's, partial of m minus partial of m with respect to y, partial of m with respect to x, all over n, the original, not this, the original. Saw that a lot with a lot of students. They'll be like, hey, this divided by this, sorry, this minus this over that, or this minus this over just that number. Make sure you're going back to your actual n. So when we're doing this, we're taking the 1 minus the -1, which is not 0, over the n, that negative x. Don't do this minus this over that. That's not what that's asking you for. That's asking for the partial derivatives over the original piece n. That's what that's saying. Which says, oh, that's actually really nice. That's 2 over negative x, or -2 over x. Ask yourself, is that your integrating factor? No, but what we're doing is to find an integrating factor, we're going to have to integrate and take e to that to find the factor. So long story made real short, that's not exact. It shows it right here. Let's take our mixed partials, put them in a relationship that's going to work for us, and say, hey, if I have only x's, that's awesome. I'm done. Don't do the next one. Why do the next one? This will work just fine for us. If you did the next one, you'd take -1, -1 would be -2, but you'd have to divide it by m. And that's going to have both x's and y's. It wouldn't work for you anyway. So find one of those things that's either x's by taking first the derivative with respect to y minus the derivative with respect to x all over n, or flipping that around, that should be only y's. So for us, we go, yeah, our u is really nice. It's an e to the integral of negative 2 over x dx. That gives us this e to the negative 2 ln x. That gives us, and you can probably see this, e to the ln of 1 over x squared, or just x squared. So our u is just x squared. Let's see how that flies. What we're going to be doing, that's not true. What we're going to be doing is we're going to multiply this entire differential equation by 1 over x squared, and it is going to change it into an exact differential equation. So let's do it. X to the fourth minus x plus y all dx plus negative x dy equals 0. We know that. And we're going to take and multiply all of this, distribute through everywhere where we need to, by our integrating factor of 1 over x squared, and let's see how that works out for us. So I'm going to move up there and get x squared. We're going to get minus 1 over x. We're going to get y over x squared dx plus, let's see, negative x over x squared. It's 1 over x dy, and still equal to 0. You multiply by 0, function of x. X cannot be 0 here. X is, x cannot be 0 here. And so let's go ahead, let's test it. Let's see if it's actually an exact differential equation by finding our mixed partials. This is our new m, and that's our new n. Well, when we try it, the partial derivative of m with respect to y, 0, cool, 0, 1 over x squared. Partial derivative of n with respect to x. Let's see, this would be negative 1, x to the negative 1. Let's bring down negative 1 to be positive 1. Subtract 1, it's negative 2, but move it down. That would be positive 1 over x squared. Oh my gosh, it worked. Hey, it's gonna work. It's good, I promise. Proved it. So if those are the same, that means the mixed partials are equal. I use different notation just to make you aware of that, to reinforce that we're dealing with the same thing. This is m sub y. It's the same exact idea. I just wanted you to see it, to reinforce that concept. So now that we're over this is now basically irrelevant. Besides the domain issues we have to impose on it, this is basically irrelevant. And we do this process from here down exactly like any other exact differential equation. We pick the piece that's easier to integrate. So what would you pick? Would you want to integrate this with respect to x? Or this with respect to y? Yeah, that's a lot easier. So our derivative with respect to y, this is our n. This is negative 1 over x. That's exactly what that means. So if this is an exact differential equation, which we just said that it was, then this piece has to be the partial derivative of f with respect to y. Let's integrate with respect to y, which means our function, in terms of x and y, is going to be an integral of negative 1 over x dy, not dx. You know that a lot of students get confused here, right? They go, oh yeah, that's going to be, oh, that's a negative ln x. It's not. You're integrating with respect to y. Look, if your partial derivative of f with respect to y is this piece, you're undoing the y derivative with respect to y. So you're taking an integral with respect to y. Now, what is that? Actually, it's a really nice thing. It's just, well, if negative 1 over x would be held constant, it'd be like, let's say negative 2. You would get negative 2y. So we're going to get negative y over x. But we are going to get a function that could have x's in it, because under a partial derivative with respect to y, all of these x terms would be completely gone. So we took an integral of this with respect to y, we tacked on a y. And we also said a constant, all terms that would have x's would be held constant under a partial derivative with respect to y. Let's take the partial derivative of f with respect to x. What we're going to do is when we take the partial derivative of f with respect to x, we're going to know that since this is the function we're looking for, the partial derivative of that function with respect to x, the variable opposite this one, has to be set equal to that piece. You see, this is the partial derivative of f with respect to x. So we're going to take it and set it equal to that. So partial with respect to x, that's a positive y over x squared. But the first derivative of h with respect to x, we did take a derivative of that. That piece has to be equal to our m because that's how m is defined. M is the partial of f with respect to x. All of your terms with y in it have to cancel here, just like all your terms with x's had to cancel in the last example. So these two, they have to go away. If they don't, you've done something wrong. So the first derivative of that piece that we're looking for that has only x's, hey, only x's, we get x squared minus 1 over x. And how we undo these derivatives is with integrals. So the h of x is the integral of x squared minus 1 over x dx, which means we're going to get 1/3 x cubed minus ln x. Now, I'm going to not have that absolute value there because we can drop it from over here. That's where the x came from. That's what I was talking about a little while ago when we talked about how your integrating factor really doesn't affect how you do the problem, but it could affect your domain. So watch out for that. We'd say things like assume positive or not zero where necessary. Because we have the x squared on our integrating factor, that's going to keep that positive for us. And man, that's it. We're just going to put this back in the function. So we integrated n with respect to y, then derivative with respect to x set equal to m. So n integrate derivative m. We solve that and we know that our function of x and y, it was here, but we had a function that was x's that we didn't know. We just found that function of x's. And we know that has to be equal to a constant. A couple other things that you can do. Sometimes you will see this solved for y. So is this okay to leave it like this? I would say sure, that's of the proper form, but sometimes you're going to see that solved for y. So let's practice that right now. What we might try to do is multiply everything times x. So if we multiply everything times x, we would get just negative y, 1/3 x to the 4th, minus x ln x, and then cx, a constant x. And if we add our y and subtract our constant x, which is subtracting that constant, you know what we're going to do, right? We're subtract cx, we're going to change that minus c into just a plus anyway. We would get this, I'm flip-flopping sides here. I'm adding my y, I'm subtracting my cx, which is just fine. So 1/3 x to the 4th minus x ln x plus c of x, and then when c times x. When you get to the back of the book and you say, wait a minute, why is that a plus? What the heck? It's because they're saying, let's suppose that c equals negative c, and then you will see probably this, because it's an arbitrary constant, the sign doesn't matter for us. Man, I hope that makes sense. I hope that you're with me on the fact that once you find your integrating factor and use it, you will get an exact differential equation. It's going to happen. And you solve it the same exact way. You pick whatever's easiest, m with respect to x or n with respect to y. Whatever one you choose, you're going to be integrating, getting a constant that has the opposite variable, taking a derivative with respect to that variable and setting it equal to the opposite piece you just to the thing that you just integrated. So if you picked m first, you take a derivative with respect to y, and then you set equal to n. You pick n first, you integrate with respect to y, take a derivative with respect to x, and set equal to m. And then that's the rest of it's pretty nice. We're going to come back with one more. I hope that's making sense. I hope I'm explaining it well enough that you understand. It's always my goal here. So Hang on for just a moment. You know what? I need to correct something. I had this wrong in my head. After thinking about it, this integrating factor does affect the domain, but only on the integrating factor. The fact that that x squared doesn't need the absolute value. I was wrong over here, so I want to correct this right now. When we get down to here and we say, hey, this doesn't need an absolute value, it's because we're squaring that. We're squaring that x. And the absolute value squared, no matter what that x is going to be positive. But I was wrong here. So when we get down to this integral, we can't assume that that x is always positive. And so what we would say is we need the absolute value of that. The absolute value is necessary. My mistake, I'm sorry, but I noticed it right when I was about to do the next example. And so we would follow that all the way down, and you're going to end with an absolute value of x there. My apologies on that one. I had my brain not straight. So I hope that makes sense now. Maybe that clears something up for you. I do try to leave these mistakes on the videos for the main reason to show that it's going to happen. It does happen, and hopefully you're learning from those mistakes. So I make them too. Obviously, I just did, because we can start thinking a little bit wrong, but that's why it's important to go back and check your work. And so you look at it and you go, okay, let me go through this one more time. That's what I did. I paused for a second, I turned off the video, and I looked and said, wait a minute. No, that's positive. That's positive because of that power 2, but that doesn't affect this ln of x. And so we need the absolute value there because those two things are not, this is not guaranteeing over here, this is not guaranteeing that x is positive. We need to make sure that the ln has only positives in it. So again, hope that makes sense. Hope you're learning from my mistakes as well. Okay, we'll be back with one more example. Let's take a look at this one. Do you see the first thing you might do? The first thing, you're probably thinking, I'm going to check mixed partials, and you're absolutely right. But right before that, you might take the time to write this as the proper form if it were an exact differential equation, which means that really should be a plus. And we saw last example that sort of impacts our mixed partials to make sure we're taking that sign with it. So you might see this a lot. Let's just write this as the proper form. If it were an exact differential equation, it would look like this. And we can now see that, all right, let's define it. Let's say that this is m and this is n, and yeah, and now you check your mixed partials, and let's see what happens. So if we take our mixed partial derivatives, m with respect to y, we're going to get 2y plus 2x. This with respect to y is 2y, this with respect to y is 2x, and then partial derivative of n with respect to x is negative 2x. He said those aren't the same. Yeah, exactly right. So if those are not the same, that is not an exact differential equation. It's some potential function right now. We are going to find an integrating factor to make it happen. Try it now. Actually, what I encourage you to do, try it in your head. At least check. If you took this minus this and divided by that, so this minus this, that would be 2y plus 4x over that. Is there any possible chance that's going to get rid of your y? And the answer is no, it's not going to work. So I'm going to show that to you, but you can eliminate that right now. This is not going to be an integrating factor with just x's. This is going to be, if possible, an integrating factor with just y's, but here's how we show it. So for maybe just x's, we'd say let's take first derivative, or the derivative of m with respect to y, that's 2y plus 2x, minus the derivative of n with respect to x, it's negative 2x, and we would divide that by n. So that's here, that's negative x squared. Since this gives us 2y plus 4x over x squared, that y is not going to simplify for us. Nothing that you're going to have both x's and y's. This is not one we want to deal with. So we're going to say, no, that's not the way to go. Let's do the next one. Let's just switch this around and divide by something else. So let's try for y. That would be negative 2x. So we're doing the derivative of n with respect to x minus derivative of m with respect to y. Yes, you need parentheses. So we're taking this minus this whole piece, minus both terms here, and dividing it by m. That doesn't look very nice. Well, let's simplify it. Let's see what can happen. If we do simplify it, this will be negative 2x minus 2x. That's negative 4x minus 2y over, well, let's see, y squared plus 2xy. That's not too bad. Maybe we try to factor that. So let's factor out a negative 2 and get 2x plus y. Let's factor out a y and get y plus 2x. You go, oh, I know about commutativity of addition. I know that these are exactly the same and I can simplify them. And that gives us a function that's just in terms of y. That's what we're looking for, folks. We don't want to mess around with both variables. So we try the x first. If you have both variables, no, forget it. Reverse, do the opposite subtraction divided by the opposite piece. And so we'd say either this minus this over this, or this minus this over that. And that's exactly what we're doing here. And so when we got that negative 2 over y, that's not your integrating factor, but it's the way we find it. So our u is e to the integral of negative 2 over y dy. U is e to the negative 2 ln y. We know that this is going to be e to the ln 1 over y squared, and then u is just 1 over y squared. So we're going to get 1 over y squared. That's what we're going to multiply our differential equation by to make it exact. That's an integrating factor. So what we had, let's see. We had this y squared plus 2xy dx. Are you with me? I hope you're with me. Plus this negative x squared dy equals 0. Now we're saying that wasn't exact, but because we had this nice proof over here, we can take this and we can multiply it by an integrating factor, this time with just y's in it. We tried x's, it didn't work. We tried y's, it did. And that is 1 over y squared. So we're going to distribute, and that's going to distribute through to all of our terms in that factor, which means we're going to get 1 y squared times y. Remember, we're distributing here, here. That's going to distribute through. So 1 plus 2x over y, that would be our dx, plus negative x squared over y squared, that's next to our dy, and still 0. Can you follow it? Can you do it? Because right now we're going to check to see if that's an exact differential equation, and it's going to be. But what that's going to say to us is that we're going to start basically like 2 problems in one. Find your integrating factor, verify that this is your new m and this is your new n. Verify that those things, I'm going to use different notation here to keep you comfortable with it, that those things, the partial of m with respect to y, and the partial of n with respect to x, make sure those things are equal, because that is telling you that you did it right. That's the way to check your work. So you don't just do this and then go for the integration. You do this, you check, you check what your mixed partials are. You got to use them anyway, because what you're going to end up doing is you're going to integrate one of these, right? Then you take a derivative and set it equal to these pieces down here, your partial derivatives anyhow. So you got to find them anyway. You may as well check right now to make sure you've done this part right, so this part's not a waste of time. So the partial derivative of m with respect to y, that actually is a constant, so 0. This is going to give us a negative 2x over y squared. And the partial derivative of n with respect to x is negative 2x over y squared. Hey, it worked. Of course it's going to work. It has to work if you've done this right. If not, it's going to show up right here. And then you go, oh man, I probably made a mistake back here. Let's check that, and let's see that I get my integrating factor right. This is awesome. Now we take a look at it, and you tell me, man, think it to me right now in your head. Which one's easier for you to look at? Would you want to integrate this with respect to x, or would you want to integrate this with respect to y? I don't see that there's much of a difference, really. This you'd have 2 terms, this I don't think it makes a difference. Yeah, I'll take that one today. So if I'm going to integrate, so if I know that the derivative of f with respect to y is n, so this is your n. If I know that n is the derivative of partial derivative of f with respect to y, then that is this negative x squared over y squared. Then our function is the integral of that. But just watch out. This is the partial of f with respect to y. You're undoing a partial with respect to y. That means an integral with respect to y. Okay, let's do with respect to y. Integral of negative x squared y to the negative 2 dy. What in the world is that? Let's see. That's that we add 1, so that would be negative 1 divided by the new exponent of negative 1. So our function is going to look like this. We're going to have this negative x squared y to the negative 1 over negative 1. We're going to clean that up, of course, but we do have a constant. We do have a constant in terms of x. So that partial would say any terms of x are gone. That's why we have a constant that could have x in it, because we got this from a partial derivative with respect to y. So let's make this a little nicer. So our function says negative, that would be x squared over y. And plus h of x. Okay, now what? Now that we have the function itself, so this is our answer. It really is. There's just a piece we don't know. So if this is really our answer, we have a piece we don't know. Let's use some part of this to figure out the piece. So we know that we used n with respect to y. We got our function. Let's take a partial derivative of f with respect to x, and that's got to set equal to our m. So try that. Partial derivative of f with respect to x. Okay, with respect to x, that would be a 2xy plus h prime of x. The derivative of all that function of x that we don't know. And that's got to equal, man, this piece is what m is. So that's got to be 1 plus 2x over y. That's got to be that. If we subtract that 2x over y, kind of cool, we get the first derivative of h with respect to x is just 1. Those pieces are gone. Let's see, how we do undo derivatives? Well, we do integrals. So let's integrate with respect to x. Man, we just get x. That's nice. So let's see. We integrated. We actually found our function right here. We were done. We found our function. The problem is there's a piece we didn't know. We took a derivative with respect to x, partial, and that let us set equal to m. We got rid of everything that had y's in it. We integrated the function of x that was remaining, and we have h of x equals x. Let's plug that back in. So our function is, that's x squared over y. Plus x equals some constant. All right, well, that means that x squared over y plus x equals c. That right there is a potential function that would give us this exact differential equation. It's fantastic. The other thing that I want to talk about is sometimes they'll make you solve that for y. So if they do that, you'd have to subtract x. And then we can multiply both sides by y, divide both sides by c minus x. One thing I do want to mention here, we're not going to cover explicitly now, but we'll talk about it later, is that when you use this type of a solving technique, this integrating factors, sometimes you can get extra solutions. Sometimes those work and sometimes those don't. And sometimes you can miss solutions, like singular solutions. So be careful of those. That if you're seeing some things like, oh, I'm not so sure. We talked about singular solutions a while ago. I mentioned a blurb about it, and I'm going to do a video on it about exactly how to find those a little bit later. But I want you to just be aware right now that sometimes you can gain solutions or not find all of the solutions with these techniques. We talked about that a while back, how some of our techniques don't give us everything, like singular solutions of like 0, for instance. So be careful of that. Just wanted to tell you a blurb about it, but I hope this video was enjoyable for you. I hope you learned this new techniques. A lot of classes that I've seen teachers teach, they don't even talk about this. So hopefully that was kind of neat for you to see how a different type of integrating factor worked. I mentioned how there were other integrating factors besides just doing the ones with what we've done so far, and now I got to show to you, so that's fun. Okay, hope you enjoyed it. Hope it made sense, and I will see you guys for another video coming up soon when we start talking about some real life applications. Have a good day.